So to simplify expressions with exponents, including our rational exponents, there are 4 steps to be able to have a simplified monomial expression. You can't have any powers of powers. Each base can only appear once. All fractions are in simplest form, and we can have no negative exponents. Number 4 is the most common one that people forget about. So make sure you are checking that your answer doesn't have negative exponents. So these coefficients in front can be multiplied. 2 times negative 4 gives me negative 8. And when we have exponents and their bases are being multiplied, we add those exponents. A lot of these exponent rules are ones that you may have seen in Algebra 1, so this is a review of all of those exponent rules. 3 plus 2 gives me 5. Then I have b to the negative 2 and b to the 4th. We'll add those exponents because the bases are being multiplied. So negative 2 plus 4 gives me positive 2. This meets all 4 of the criteria up there, so that's our answer. For number 2, we have 12 over 2, which is 6. And then when I have exponents whose bases are being divided, we subtract the exponents. And I like to subscribe to the theory of doing the big number minus the small number and put your answer where you found the biggest number. So in this case, I have 4 on top and an exponent of 1 on the bottom. So I would do 4 minus 1, which is 3. And since x to the 4th was bigger and it was on top, x cubed will be where I put my answer, on top. 5 minus 2 is 3. And since the 5 was on the bottom, y cubed will be on the bottom. It meets all 4 requirements. So we'll move on to number 3. You always want to try to simplify inside the parentheses first, but the only thing that I can do is raise c to the 0 power. Anything raised to the 0 power is just 1. In fact, it's the easiest one that you can check on your calculator. You can just type any number to the 0 power and it would always be 1. So if you can't remember, check it on your calculator when it comes time for the assessment. That's the only thing I can do to simplify inside. So when I have powers that have been raised to another power, I need to multiply all of those exponents. Now there's actually 4 exponents inside here. Each one of these that you can't see an exponent for has an exponent of 1. I really recommend you write that exponent of 1 so that you don't forget to multiply those exponents. So I have 2 to the 1 times 3, or 2 times 3, 2 to the 3rd. A to the 2 times 3, or a to the 6th. 3 to the 1 times 3, or 3 to the 3rd. B to the 1 times 3, or b to the 3rd. We're going to simplify one more step by finding out 2 to the 3rd is 8. And 3 to the 3rd gives me 27. Once it meets all 4 steps, we can move on to our next problem. There are 3 exponents in here that I'll have to distribute that 3 to. 6 to the 1 times 3 gives me 6 to the 3rd. G to the 5 times 3 gives me g to the 15. And h to the negative 4 times 3 gives me h to the negative 12. Now this does not meet all the requirements because number 1, I need to tell them what 6 to the 3rd is. But number 2, I have a negative exponent. So I need to get rid of that negative exponent in my answer. 6 to the 3rd is 216. Then I have g to the 15th. And to get rid of a negative exponent, it has to cross across a fraction bar. So negative 12 is my exponent, and it's in the numerator, so it will have to move to the denominator to become positive. Now it meets all 4 requirements of a simplified monomial, so I'm done. For number 5, I can simplify this 24 over 3. It becomes just 8. And then inside of these parentheses, the only thing I can do is say a to the 0 is 1. So I will take each of the exponents and multiply them by the power outside. So a to the 8 times 3 gives me a to the 24th. b to the 1 times 3 gives me b to the third. b to the 1 times 3 again gives me b to the third. This is not yet simplified because I have two of the same base. So I need to do exponent minus exponent. 3 minus 3 gives me 0, and anything to the 0 power is just 1. So my answer is 8a to the 24th. For number 6, this is kind of where the Algebra 1 material crosses over into Algebra 2. We have 2 over 54 that will need to be simplified, and that becomes 1 over 27. Then the a's will subtract the exponents. 4 minus 3 is 1. 4 was bigger, so a to the first goes to the bottom. 6 minus 5 is 1, and since the 6 was bigger, b to the first goes to the bottom. Now that did not unfortunately get rid of my radical or get rid of the fraction, so I will need to go ahead and separate these out into their own radical. So cubed root of 1 over cubed root of 27, a, b. Now the cubed root of 1 is just 1. The cubed root of 27 is 3, but I still have a cubed root of a and b, and we cannot have any radicals in the denominator. So to get rid of that radical in the denominator, we'll need to rationalize like we did in the previous lesson. There needs to be 3 of a number to be able to come outside of the radical. I have only one a and one b, so I'll need 2 more of each to be able to come outside of the radical. So a squared and b squared will need to be multiplied on top and bottom. So on the top, we just have cubed root of a squared and b squared. And on the bottom, I have a 3 that I already took out. And now I have 3 total a's, so a can come out, and 3 total b's, so a b can come out. So that's what happens with integer exponents. Let's learn about our rational or fraction exponents. When converting between radical form and rational exponent form, we have an index outside, and we have this exponent inside. So to convert, we will need to put the exponent over the index. Same as what we've been doing when we've been simplifying all of our radicals. What does that look like? Well, if I had 10 to the 1/4 and I wanted to convert it into radical form, 10 would be what's underneath a radical, and the exponent for the 10 would be the numerator, and the index would come from the denominator, so 4th root of 10. For x to the 1/5, in radical form, I need a radical, and the x is the radicand. The exponent is the numerator, 1. The index is the denominator, 5. So 5th root of x. Then I have radical form into rational exponent form. 15 is my base. The exponent is 1, invisible exponent, over the index, which is 3. For number 4, each of those numbers will become their own base. 7 has an exponent of 1, x has an exponent of 6, and y has an exponent of 9. Those are all of the numerators, and the denominator is the index. One of the benefits of doing this radical form and rational exponent form is that I am able to simplify further, or sometimes these fractions, I can write them with equivalent fractions and get them underneath a single radical. For example, if I had a fraction that was 3/2, which is the reduced form of 6/4, I could have rewritten this with a common denominator and been able to write it underneath a radical. Or similarly, if I could simplify it outside of the radical, I would reduce those fractions. Let's do some simplifying with rational exponents. They follow the same rules as our integer exponents. So we have a to the 3/4 and a to the 1/2. We'll need to add those exponents together. 3/4 plus 1/2. You can let your calculator do that because you'll need to find a common denominator, or if you'd like to do it by hand, that's fine as well. You should end up with 5/4. For number 6, these bases are being divided, so their exponents will need to be subtracted. 4/5 minus 1/5 gives me 3/5. Multiplying fractions, that's no problem. It's the top times the top and the bottom times the bottom. So I'm really just simplifying one larger fraction. I have b to the 3 minus 1/3 and c to the 1, exponent of 1, minus 1/2. So we'll simplify that and get b, there we go, b to the 8/3 and c to the 1/2. Now we could, if we'd like, rewrite this with a common denominator so that I could write it into radical form, but that's not necessary at this point. Turn the page. Look at number 8. So with number 8, when we are working to simplify these, we're going to write them in rational form, 9 to the 1/4 and g to the 2/4. And the benefit of writing it this way is that I can reduce that 2/4 to be 1/2. So I have 9 to the 1/4 and g to the 1/2. In looking at number 9, the first thing that I might be tempted to do is go ahead and do my prime factorization or my factor tree. So for 64, if I did a factor tree for 64, I would have 8 and 8, then 2 and 4, and 2 and 4, then 2 and 2, and 2 and 2. So I'm looking for 5 of the same number. 1, 2, 3, 4, 5 of the same number to come out. And I have fifth root of 2 remaining. Now in the denominator here, I have the fourth root of 4. We know that a prime factorization of 4 would just be 2 and 2. If I need a total of 4 of them to come out, I need to multiply by the fourth root of 2 squared on top and on bottom. So that gives me a total of 4 2's to come out on the bottom. And on the top, I cannot multiply these two together yet because they have different indices. That's why we would take and write them in rational exponent form. So I have 2 times 2 to the exponent is 1, index is 5. And here we have 2 to the exponent is 2, index is 4. Now, I would recommend reducing this fraction before you find a common denominator. So reducing that fraction would give me 1 over 2. And remember, when the bases are the same, we can add the exponents together. So I have a 2 on top and a 2 on the bottom that will be able to cancel. And these two, 1/5 plus our 1/2, find your common denominator of 10, and we would be at 7/10. And you can just type that into your calculator. Or you could write that in radical form, which would be the 10th root of 2 to the 7th. Either way. For number 10, we need to multiply those exponents. And this 2 has an exponent of 1. So I'd have 2 to the 1 times 4, or 2 to the 4th. And 3 fifths times 4 gives me 12 fifths. The only other thing that I need to do here is 2 to the 4th power, which is 16, and x to the 12 fifths. And that's as far as I need to go.